So faults and fractures is a plugin to OpendTect Pro. It combines all the attributes, filters and utilities that we have for fault and fracture analysis in OpendTect. The main attribute here is fault likelihood, and its derivative SINT fault likelihood. Unique to the DGB solution is also that we have a solution for basement fractures, and in certain basins fractures occur as very steeply dipping reflections. So you can't use the fault likelihood attribute, but we have an attribute that is based on fault likelihood that actually follows these very deep, steeply dipping reflectors. We have basement fractures likelihood and its derivative, the SINT basement fracture likelihood. Then we have a number of attributes which are also quite useful for fracture analysis. Two of them are fracture density and fracture proximity. We have automated fault plane extraction tools, and we have a very powerful edge preserving smoothing filter. Very often people say yes, thin fault likelihood is a very nice attribute, but it produces so many small elements that is there a possibility to filter it. So can we get rid of the smaller things? And in OpendTect, yes, you can do that. The workflow is through the automatic extraction of fault planes, because in that automatic extraction of fault planes you already set a minimum size for the fault planes that will be extracted. And that is one element of the workflow. And the second element is that we have, once the fault planes are extracted, a number of sliders that can be used to minimize the number of elements that you really want to convert into fault planes, and also which you want to resave as thin fault likelihood volume. And these sliders I can just use to reduce the very small ones, get rid of them. I can use them to only select faults in a certain direction or only dipping in a certain dip range. And then when I'm done and I've selected all the ones that I want to keep, I can save these skins again as TFL, as thin fault likelihood volume. Now there's a visualization tip here. If you display TFL on sections, it's often very nice to look at, but if you display this on time slices or along horizons, the visualization is a bit hampered because the TFL attribute is so thin, it's just one sample thick, that you can hardly see it. And then we use this trick. We use our attribute engine to beef up the TFL values again by computing an RMS in a very small volume surrounding each TFL value. And that gives very nice displays in the horizontal slice domain. Here we see an example of filtering the thin fault likelihood. So on the left we have left upper corner. Let me put a laser pointer here. In this image we see the input seismic. Here we see the TFL as computed by the algorithm. Then we go to this filtering option. We get rid of the smaller elements. And you can see here on this time slice it's difficult to see where these faults are. So then we beef it up with the RMS filtered TFL, and then we can see all the larger faults, and we have, compared to this one, removed a lot of the smaller stuff that we didn't want to see. Examples of fracture density on the right and fracture proximity on the left. Fracture density gives me the sweet spots on the in the data. Input is the TFL response. This is with different cutoff values, and here we see where we have most of these TFL values, and because that is where it is mostly broken, it's also that is where we find the largest number of fractures. The opposite of the fracture density is fracture proximity. Here we see where we have clean seismic data without any TFL responses. So that is what you would like to drill, for instance, in geothermal development in the Netherlands. You want to stay away from the faults, and you want to stay only drill only in the undisturbed areas because of seismicity problems. Now, an example of filters. The first one is our edge preserved smoothing filter. This is my input seismic. As you can see, it's quite noisy. And here we see the edge preserved smoothing result. Look at this fault, and also here, these faults over here. Toggle it a couple of times. Input, EPS filtered. Now this is compared to our standard dip steered median filter, which also has edge preserving properties. It removes random noise, but it is not smoothing the data as much. This I could still use for quantitative interpretation because everything is well preserved in terms of amplitude behavior. It's just a little bit shuffled, and the edges are not as well preserved as in the EPS volume, but it's still edge preserving. Either input we can use for fault likelihood or thin fault likelihood computations. Now then a few slides on machine learning and diffraction imaging, because machine learning, obviously we have also tools to predict faults, and some of these tools are delivered with the software in the form of pre-trained models. I will show you just one example or two examples here. On the left we have input seismic, and this is the application of a UNet fault predictor in three-dimensional fault predictor, and this is after thinning. So what happens here is that this model takes a block of seismic data, it passes it through the trained model, and the model knows how to transform this into fault likelihood. And the block is a similar size as this one, and we do that block by block. We splice the blocks together and we have our machine learning fault prediction volume. Here we see another model which is interpolating seismic traces. FaultNet is our best fault predictor. It's a three-dimensional UNet, and this output here is not thinned yet, so this is the fault likelihood as predicted by the machine learning model. Then we also offer a diffraction imaging service. Diffraction imaging is, or this service is offered in association with Moser Geophysical Services. Jan Moser is really a guru on this in this field, and the technique that he has developed is splitting the seismic input, pre-stacked depth migrated seismic input, into a reflection seismic and diffraction images. And these diffraction images are very high resolution. They pick up the fractures and faults at the highest possible resolution. The technology developed by Jan and his colleague Mike Pellissier is also integrating interpretation services. They call it customization to interpretation, and they use the processing and they tune it in such a way that you see the optimal results from an interpretation perspective. This type of technology is ideal for detecting fractures in carbonates, in basements, and in stratigraphic features, to highlight these as well.